Well, for optics, we need to get a very important relationship for physical optics, and that's the relationship between the intensity of the electromagnetic radiation and the intensity and the magnitude of the or the amplitude of the wave, I should say. So let's take a look at that. We'll have to look at energy or energy densities concepts. But as we've seen, I have a plane wave now that's propagating in this direction, and I'm using this representation, the sine. So everything here is real. It's propagating in the k vector direction, so there's k vector. The speed, it could be a medium, and so the wave velocity is the square root of epsilon mu. I remember we found that all of these vectors, k, b, and e, E naught, B naught, and K are all mutually orthogonal. So if this direction is K, I chose the Y direction here to be, well, I choose this direction to be X, choose this direction to be Y, and then B is actually orthogonal to it, would be perpendicular coming out. But B, remember, is much reduced from the electric magnitude. In fact, it's a factor of about 1 over 10 to the 8th of the electric field portion. Yeah. So we have that. Now let me rotate around so that I'm looking at this electric sinusoidal wave right at the usual fashion, moving with speed v in this direction. So electric field, pretty obviously, is either up or down. It's in the y direction. And B is perpendicular. K in this case is K in the x hat, so it's propagating in the positive x direction. And B is perpendicular to both the plane of the electric field and K, and so that's going to be coming right out at us as the direction of B oscillating toward us or away from us. Anyway, if you put all that together, we can get an explicit representation for the electric field. It's going to be its amplitude in the y hat times the sinusoidal. B vector is going to be this constant amplitude in the z direction that's coming out of the page at me times the same sine function. And if I've got the electric field and the magnetic field, I can calculate the energy density. That's the energy per volume in the electric field. And if you remember, that's 1 half epsilon E squared plus 1 over 2 mu times B squared is the electromagnetic field energy density. And energy density is if I've got an amount of energy delta E in the volume delta V, then the energy density is energy per volume. So this turns out into joules in SI units, turns into joules per cubic meter. And I can just plug these expressions in for E and B and do some straightforward simplification. I can square everything. 1 half epsilon E squared, this dot product is E squared is simply the magnitude of it. Sine squared, then be a similar result. And then I can use the fact that up here that B and the magnitude of B and the magnitude of E for these plane waves are related by a factor of 1 over the velocity. And so I simply substitute for B here the magnitude of E over the velocity, and that gives me E squared over the velocity squared for that term. And then I factor out, well, a little algebra, I guess, and then factor out. If you look at this, I've got some common terms. I've got a 1 half. I've got an E squared in both of these. I've got a sine squared, so I pull the sine squared this way, a 1 half E squared, and then I'm left with epsilon plus, I factored out the 2's in both cases, 1 over mu times the velocity squared. But remember, the velocity is 1 over the square root of epsilon mu. And so I plug that in here and then reduce. The epsilon mu will, when I square root, will become epsilon mu. That'll flip over on top, and then the mu's cancel, and this term then just becomes epsilon plus epsilon, or 2 epsilon. And that cancels the 2 there. And so I get for the total electromagnetic field energy is expressible as epsilon times the magnitude of the electric component. I don't have to worry about the magnetic component. There's no approximations in this. We've accounted for the magnetic field over here. It just turns out that the half cancel, or the half goes away in this with the magnetic field portion of the energy. And then remember, so there's one expression that not that useful except in getting our expressions for the intensity. So let's look at the intensity. Now remember, the intensity here is delta E is the energy per area per time. And the picture, remember, if I have light shining on a piece of material that actually transfers energy to it, it depends on how long you're shining it. The area could heat up, for instance. But I hit an area A. If I look at this in cross-section, this is the definition, the amount of energy that hits this in time delta T. So this is the energy delta E that hits in time delta T. And divide that, so it's the energy per time that hits the area A divided by the area is, by definition, the intensity of the light. And in our case, we can, all the light in time delta T that is going to hit here is going to be delta x v delta t, where v is the velocity. So I go out in front of this by a distance v delta dt, and that is dx. What I do then is I multiply top and bottom by the delta x. But delta x over delta t, that's just v delta t times delta t, and the delta t's go out. So I think we got this expression maybe before in a different context, but the intensity turns into the energy density, in our case electromagnetic field energy density, times the wave velocity. If it's in a vacuum, this v, of course, is c. And if I plug in our expression for the energy density up here, that expression, I get the intensity at any point in space varies in this fashion. And what I want is I want my area here to be the area of my detector. It could be my eye, or it could be a photo detector. It could be a photoresistor, something that we're using to measure how bright the light is here. It could be a photocell or a solar cell. Different terminologies, different kinds of detectors. Could be a photomultiplier tube that is there. So different kinds of detectors. Could be an eye. And what I'm going to do is I know that the intensity varies like this everywhere in space, but I only want it what the intensity is at my detector. So I'm going to set my origin at x equal to 0 here. And when I do that, this reduces to, well, if that's equal to 0, it's really sine of minus omega t, which is minus the sine of omega t. But since it's all squared, it's the same as sine squared omega t. And then you see really a major issue. Because this intensity is varying sinusoidally in this fashion with time, or sinusoidally squared, in this fashion with time. And unfortunately, this omega here, that's on the order of 10 to the 16 or 17 hertz. So it's varying very, very rapidly, and there's no detector that can respond quickly enough to actually generate this plot of this function here. Here it would come up, come down, come up, come down. Everything here is positive. This is the plot of this sine squared. Usually it has a maximum intensity, which is the stuff out front. And so I have the I naught, and it's going to vary like this. If I had a detector that could actually instantaneously calculate it. But remember, this is a very, very short time period. It's on the order of 10 to the minus 16 or 10 to the minus 17 seconds to get to this point, somewhere, something on that order, depending on the precise frequency of the light. And no detector can respond that. So what do? Well, what you do is the eye or a detector does respond, but it does sort of a time average. And so one takes the time average really over many, many periods, maybe a second worth, or a millisecond, which is huge compared to 10 to the minus 16 seconds. So in either case, we have that. And we define the time average of the intensity as this integral of the intensity uh, over time from over one period divided by the period. Or I could take 10 periods, integral from 0 to 10 periods divided by 10 times t. Or I could take 10 to the 16th periods uh, because ultimately it's going to reduce to exactly the same number. And you may notice the way I've drawn this. It turns out that the the area underneath the I of t curve is just 1/2 I naught, and the whatever the maximum is. And what happens is all the area that's in this portion above the half gets filled in here. This portion gets filled in over here, and so one has an average value of 1/2 I naught. You can do this integral here with respect to t, but again, what you'll find is you'll get this factor of a half there. So we get our factor of a half back. Since I naught was epsilon e squared v, I can plug that in here, and we get the intensity as measured by a detector. It's really the time average intensity is given by this expression. Here, epsilon, well, I've got it in a vacuum. In general, this would be a epsilon for the material, if it's epsilon naught. And then if it's in the vacuum, well, V is equal to C here. The important thing for us is this time average intensity is equal to, or is proportional to, the electric field amplitude squared. And we'll use that expression over and over again to get interference patterns, and just the fact that it's a couple of constants here times that amplitude squared. Again, if it's a vacuum, well, then this becomes C, and you may see that expression as well.